Today we're going to learn about three gas laws, and we're going to start with Boyle's law. Remember, we talked about the variables that can change pressure. That's volume, temperature, and number of particles or moles of particles that you can put on. Why? Because pressure is all about the number of collisions I can make happen on the side of a container. So, Boyle's law is about pressure and volume, and all the other variables we talked about are held constant. We have the same number of particles in my drawing, 1, 2, 3, 4, 4 moles of gas, and over here we have 4 moles of gas. This is like a syringe. This is a piston that you can push down. So here the piston's pushed down and my gas becomes closer. So which one of these containers would we have more collisions on the side of the walls? They both have 4 particles. All 4 particles are going to hit the side of the walls. But these guys have a much longer distance to travel. So within a certain amount of time, we're going to have less collisions here, and we're going to have more collisions here. Even though it's the same number of particles, I have less distance to travel. Here would hit the side, boom, 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 boom. Here, same speed, boom, 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 boom. But less distance to travel, I'm going to hit the sides of the container faster. Okay? So what we have is we have a high volume here, V is for volume, and we have a low volume here. What does that do to the pressure? Well, we start out with pressure here, and we're just going to say that this is a low pressure, okay? And when I make the volume smaller, my gas particles have less distance to travel. They're going to hit the side of the walls more per second, so my pressure will be high. Okay, so if I have a high volume, I have a low pressure. If I have a low volume, I have a high pressure. This is called inversely proportional. Okay, so this is an inverse relationship. And what does that look like on the graph? Well, if I graph pressure over volume, inverse looks like that. And you will need to be able to recognize these graphs. So make sure you're taking good notes. What did we keep constant? Well, the temperature is the same. We didn't change the temperature. And the number of moles, which we represent is a little baby n. That means number of moles is 4 in both. So that's kept constant too. And the math formula that we're going to be using for Boyle's law is pressure 1, volume 1. That's the initial pressure and the initial volume. Then I change it to a second condition. What did I change here? Well, I changed my volume. Okay, and I get a new pressure. So let's say that I had 2 atmospheres of pressure and it was in a 2-liter container. And my pressure goes down to 1 atmosphere. Why did my pressure drop? Well, this would equal 4 on this side. So this would have to be a 4 to equal 4 on this side. Notice when my pressure went down, my volume went up. Okay, right now I just wanted to show you the math and why it is opposite. Okay? So our next guy we're going to look at is Gay-Lussac's law. And this guy just looked at pressure versus temperature. Now remember, temperature is the average kinetic energy or the speed of those molecules. So we have a low temperature and a low pressure. What happens if I increase, I still have the same number of moles, 3 moles there, and I increase the temperature? Well, these little arrows I'm going to draw longer because that just means they're moving faster. The longer the arrow, the faster they're moving. Okay? If they're moving faster, will I get more or less collisions? If they're moving faster, they'll bounce against these walls more times, so my pressure will be higher. Okay, so if I have a low temperature, I will have a low pressure, less number of collisions. If I increase that temperature, my pressure will go up. This is a direct relationship. Pressure and temperature go up together. Direct relationship. And what does that look like on the graph if I do pressure over temperature? A direct relationship is just a straight line. Okay, what did I keep constant? Well, here it's a constant volume. This is a closed container. There's no piston that can move, so the volume stays the same, and my number of moles stay the same. So let's look at this mathematically. The first thing to know is our temperature must be in Kelvin. Remember, Kelvin is directly proportional to kinetic energy. I can't get a negative temperature here. My numbers can't go negative. Okay, so we have to do the Kelvin. 273 plus C equals Kelvin. So if I have 25 degrees C, it's going to be 298 Kelvin. Okay, why? Because 25 plus 273. Let's do 273 plus 25 degrees C equals 298. Okay, so let's just look mathematically why this is a direct relationship. If my pressure is 4 atmospheres and it's at 4 Kelvin, okay, so pressure, temperature. If I change my pressure to a second condition, okay, so my pressure is now 10, oops, that's not right. 10 atm. What does this have to be? This has to be 10K. Why? Because 4 divided by 4 is 1 equals 10 divided by 10 is 1. If I increase my pressure, my temperature must have gone up to get that pressure. Okay, so this is just showing you that it is a direct relationship. Our last law that we're going to look at is Charles' law. And Charles' law looks at volume versus temperature. Now, I could have drawn a piston like this and things would move, but you guys are more familiar with balloons, okay? What did we keep constant? We kept the number of moles and the pressure constant, okay? So if I have this balloon at 25 degrees C, what happens if it's a hotter day? What happens to that balloon? Well, it gets bigger, okay? If you've ever taken a balloon and put it out in the cold air, it would shrink. Why does this happen? Well, here our temperature is low, so I have my arrows short. And here I increase my temperature to 100 degrees Celsius, and I made those longer. Well, that means they're moving faster. Remember, longer arrows faster. So my pressure increases inside the balloon, but what's interesting here is this is constant pressure. So if they were moving faster and it was this size, how do I make adjustments so my pressure stays the same? Okay, well, remember, it's about pushing on the outside and these become equal. So my volume just increases until the pressure on the inside and the outside is the same. So if my volume can change and I increase my temperature, these collisions will happen so much that the volume will expand until the pressure inside equals the pressure outside. Okay, and this is my temperature's low, my volume's low. I increase my temperature, my volume increases. So what kind of relationship is this? It is a direct relationship. Okay, and if I did volume over temperature, a direct relationship looks like a straight line. So these graphs, the only one that's inverse is Boyle's. Okay, everything else is a direct relationship, and that's just a straight line. So we have volume 1 over temperature 1 equals volume 2 over temperature 2. That's the math. And temperature has to be in Kelvin. Temperature in Kelvin. You have to do this conversion.